right. So what questions do you all have at this point?
I didn't get any of the things where it was talking about like, I don't even know, put B's on everything. I just couldn't figure it out.
Okay.
Let me try to find it.
I'm gonna pull Jesse in now first.
It looks like you guys are still muted.
There we go.
Now I can hear you. All
I know how to do this. Okay, I opened it.
right, I was just wondering what questions you all might have at this point. Let's spell all the way here.
There we go.
Yeah, I know. 14. You rounded up to 4 decimals or
24, it says, and what percentage of the top scores is this selection? I couldn't figure out like what equation would use for that.
4? Is that what you
I left 4. No, no.
So what's the consensus in terms of what equation was used to answer number 24?
Yes.
How did you all approach number 24?
Not well.
I'm going to be my really
24 is impossible.
and then found the Z-score, and I didn't know what to do after that, so I just said, oh, it's in the 16%, even though I know that's wrong.
Okay, so is there a consensus that you got to find the Z-score?
Yes.
Yeah.
Okay, so once you find the Z-score, what did you all do with that?
I just said that was the percentage. That
I didn't know what to do with it.
Okay, so the first part of it, the consensus is you figure out the Z-score. That is correct. Okay, so then the second part of it is in what percentage of the top scores is the sample mean? That's where you all stopped. That's when you turn to page 422 in the back of your book.
What?
Oh.
What?
442.
422 to the Z table.
For the Z score.
Z-score.
Okay, so you got the Z,
Yesterday.
Yes, you were.
you got your Z score, and then you're going to find your Z score in the column listed Z. And then you've got two other options. You can look once you have found your Z score. So what did people find as their Z score?
I got 0.16.
0.16? 0.16?
I got 1.28.
Can we do that?
1.2 is your Z score.
No, I forgot.
It's 1.28.
Do what?
1.28. Is that
1.28 is the Z score. And then what you're going to do is you're going to find 1.28 under the Z column. Okay. Now, are you looking for the area between the mean and Z? Or are you looking for the area beyond the Z that's in the tail?
Between the mean and Z, right?
Yeah.
Because of the way the question was
What
asked.
percentage of the top scores is the sample mean?
Beyond.
You're looking beyond the Z.
Oh.
Well, what you need to know, actually, what you're looking at, 1.28. Okay, the area beyond Z in the tail is what percentage?
I have 1.28 is
10%.
one of them. On the standard deviation.
The area beyond Z in the tail is 0.1003, correct?
Yes.
So that means from the Z-score and higher is only 10% of the scores. That's how you would interpret that, is 10%. In what percentage of the top scores is this sample mean? 10%. That makes sense how we got that.
Z-score.
I have 1.28 because I have written the Z-score on A for some reason, so usually the
Something different.
from the mean. I somehow read the Z-score at the bottom.
Okay. But yeah, so 1.28. So then we know from 1.28 and up, that it captures 10% of the scores. So below, Z-score and below is 90% of the scores.
So we use the same Z-score we found in part A.
Yes,
Oh,
yes.
so that's where I screwed up.
Yeah, that's the Z-score.
I did it twice.
You're doing more work than you
I
needed
don't
to.
even know what numbers I used to make this second. I got 8.
So does that help clarify things for you all? On that one for the moment.
Yeah. All right, sounds good. Thank you.
So what other questions are there before we move in with probabilities?
On number 14,
Number 14, okay.
should we have rounded the answers to 2 or 4 decimals?
On 14, what do you all think? What's the consensus?
Was it supposed to be a whole number? I put 4, but then I kept on thinking it was supposed to be a whole number.
I ended up with 2 whole numbers.
I ended up with 11 and 7.6. And so then I didn't know if you were supposed to round up the 7.6 to 8
I did not.
or if that was wrong.
I got 11 and 8.
Oh, which ones? I'm sorry.
14.
On number 14,
On A?
Well, we had
on
10.99.
the raw scores that correspond.
What was your formula?
They both have 2 decimals, so I don't have 4.
Decimals, 3 after your decimal.
One of the values that you're using, if it's not a whole number and you've got to round the, if you've got the 1.22 as the Z-score,
Standard deviation.
then yes, you're going to go 2 out beyond that.
Dang it.
Throughout beyond.
Yeah, because one of the original scores is has the decimal in it. We always go out 2 more spaces in the original for values that were used.
7.63. So they should both be 2 decimals.
Yeah.
Okay.
But that
So it
would
would be
make
11.
11.99 would be.
311.
Yes.
Okay. Thank you.
11 is
You're welcome.
Those were C's.
I'll have to fix that
Standard
one.
deviation plus 8.59.
They said they were decimal.
For your mean.
Anything else from chapter 6?
That's the standard deviation.
There's not an equation I have to use for part B on 24 because I already did an A. All I gotta do is look at the back.
Yep.
Yeah.
All right. So let's move on then. At least in chapter 9. You're going to get a little bit of a break from all the math.
Fun part.
Yeah, the math is fine.
Yeah. Chapter 9 is more, as if all the other chapters aren't as well, but it is more conceptual in nature, just talking about the different terminology, and it's kind of that bridge between taking our data and starting to make inferences about the population. And that's going to be based on probability. How likely, what is the probability that the scores we achieved are representative of those that we would find in the population? Okay. So it really does start to make that bridge between the descriptive and the inferential. Okay, so common layman's terms, we often interchange probability, the chances, the odds of something happening, but those are very different terms when it comes to statistics. So that's the first thing that we all need to kind of be on the same page about. So in statistics, those odds is defined as the probability that something is more likely to occur than something else. So which one is more likely to occur, this one or this one? And that's when we start talking about odds. And of course, you know, everybody is familiar with odds, especially around here at Derby. You know, the odds are 4 to 1 and that. So what are the chances of it happening versus something else happening? What are the chances that the horse is going to come in first as opposed to coming in fourth? Yeah, so we look at the odds. And because of that, because it's a probability of something happening more likely being likely to occur than something else, it's going to be a fraction or a ratio. 1 to 4, 2 to 8. That's what you're looking at when it comes to odds. Chances, though, is defined as the possibility that something will happen, just in general. What are the chances that it's going to rain today? What are the chances it's going to snow today? You hear that a lot in weather reports. 90% chance, I mean, they plaster it on the screen, 20% chance of rain today, you know, but an 80% chance of rain on the weekend. So that's where you're talking about the chances. How likely is something to occur? Not more likely to occur than something else, just how likely is it to occur? And that's going to be expressed, as you see, as percentages. What this chapter focuses on, though, is probability. And probability is the likelihood that something will happen. It's expressed as a decimal. Okay. This is the way that all inferential statistics are expressed. When you read through articles, you're going to start seeing these little p-values. That's the probability of something happening. And in research, most of the time they use 0.05, but sometimes they use 0.01. But the most common probability that you're going to see used is 0.05. Okay. And that's going to make more sense when we get into chapter 10. So, as we have already seen and talked about through the other descriptive chapters, we can start to see through graphing that there may be relationships between years. Relationship between years out of school or years since taking a math class and the anxiety level. So even in inferential statistics, while we may see a relationship, we are not proving anything. Probability doesn't prove anything. All it says is that the relationship is more likely out than in the population. So what we found in our sample is likely or not to happen and occur in the population. Now, because we can never prove anything, just like we can never be completely accurate in our predictions, there is always going to be some error in there. Just by chance. There's going to be error. And what that error or that uncertainty is what you're going to come to find out is sampling error. And what that means for our interpretation then is that all we can say is that it's more likely to happen, because there's always going to be some uncertainty about the results. So it's how likely it is to happen. Okay. So probability is based on random and chance events. Now, random, when we're talking from a statistical standpoint, doesn't mean that it's purely random. It's like, oh, that came out of nowhere, you know, or that there's no order to it, there's no pattern to the scores. What random refers to is that it's not being controlled. Okay, so that kind of plays into correlational research designs. There's no manipulation of anything. It's just random. It's just occurring. I sent you all those forms and you sent them back to me. I didn't manipulate. I didn't do anything. It just is what it is. It was random. It was naturally occurring without any interference from us as the researchers. Now, probability, in essence, is a mathematical way to describe how luck happens and how luck operates to produce things. So a sample, when we're talking about probability, our sample now is the event that occurs. The population is going to be pretty much the same, and it's going to be all possible events that could occur. Does that differentiation make sense? Okay. Okay. Now, random sampling, what do you think that would be? I mean, I know it's written here, but using that concept of randomness, what do you think random sampling would look like?
Drawing names out of a hat.
Drawing names out of a hat, perfect. Yep, that's what it is. It becomes the luck of the draw. When I was doing research out at a prison, basically that's how we selected the sample, is that I went through and they gave me access to the files, and I literally went through and started pulling them. There was no order to how I pulled them. I just pulled 30 or 40 different files, and that became my sample, I hoped. Now, not everybody had to agree to participate. They were a captive audience, but believe it or not, they were not always available when I was there, because either they'd be in a visit, or they had a meeting with somebody, or in a group, or they were in class. So a lot of things happened. So then I had to go back and randomly pull more charts in order to get enough inmates for the sample. So that's what it means. It's luck of the draw. The whole population was there. I mean, all the inmates that were there, their files were there. So I had access to all of them, and there was an equal chance that any one of them could have been selected. So if there were 1,000 inmates there, and I don't remember how many there were, every single inmate had 1 in 1,000 chances of being selected at the very beginning. But now, because I pulled that file, how many are left? 999. So the chances of the next one being pulled are going to be 1 in 999. I pull it out, keep it. So the chances, and as you can see, start increasing, because the total population is decreasing as I pull the files out. That's how they do audits. Yep. And so the random is just pulling, and that is the ideal way to get your sample. Just so you all know, is through random sampling. Because if we have any sort of control over it, that starts to change it a little bit. And that introduces possibly more error. Not always, because it still could have been that I had, 30 of, it was medium security, but maybe I had 30 charges for murders that were in there. And I had all these other, drug-related charges and that over here. So that still could have played a part, but it was random. Okay? And so for those of us here, that would be kind of the equivalent to the mess with Judge Stevens. Okay? We had a court judge who got in big trouble over here because he wanted to dismiss a jury claiming that it was not racially diverse. Now, purely random, because whoever, I've done it 3 times, it is not a fun process. But jury selection here, slew of people, they randomly call your numbers. If you go up, you go to the courtroom, they do all their questioning. Then the attorneys come up with the people they want, and then you end up with your 12 or 10 or whatever it is, depending. Well, the attorneys, apparently, I don't think they really had an opinion on this, and they ended up with a jury that the judge felt was not representative of the city.
They said because of so many more with one race than another
Right.
race.
Right.
that It's too hard for them to get people for a jury of their peers.
Of their peers, yeah. So that was kind of a recent-ish event that we had here that absolutely plays into this concept of is this jury pool representative of the larger population of everybody in Jefferson County that meets the certain requirements. So with that being said then, how do we describe these events that may or may not have occurred by chance? Well, basically the way we describe them is by noticing how often it is likely to occur when chance is involved. You're like, okay, well, what does that mean? It means we look at the likelihood, the probability of an event occurring over the long run. So we can't look at it in just the short term. We have to look at it over the long term.
So you mean to say, does this happen?
Yes, yes. For the probability, we have to look at it over the long run. Because if we base it on just the things that happened yesterday, that's not going to be a really good representation of, on average, how likely these events are to occur. Okay? Now, attempting to decide how frequently an event occurs is going to be rather subjective. That's going to be a judgment call that we as the researchers may have to make when it comes right down to it. The probability then is the relative frequency. So that's pulling us all the way back, chapter 3, talking about the relative frequencies. So out of 10 times that I've driven this street, what is the relative frequency that I'm going to make it from point A all the way to the end without hitting a red light? Now, there are portions of streets here in Louisville that happens quite often for me. So I'd say probably 0.7, the relative frequency that I'm going to make it all the way down Market Street without hitting a red light. So that's the way we describe it. But if I based it on yesterday, when I managed to hit about 2/3 of the red lights, I can't use that as my basis. I have to look at it over the past 6 months, over the past year, over the past long run. Okay? So because it's a relative frequency, as you all know, it's going to be a value between 0 and 1. And it's going to reflect the confidence that we have that an event will actually occur. So I'm about 0.7 confident, relative proportion probability is 0.7 that I'm going to make it all the way down the street and not hit a red light. Okay? So, as with all other relative frequencies, if you were to add them all up, it's going to equal 1. Okay, because that's what we do with the relative frequencies. Now, there's this little thing called the gambler's fallacy. Who is familiar with the gambler's fallacy? Anybody? Okay. The gambler's fallacy occurs when we think that an event is more likely to happen because of it not happening. So when you go to the slot machine and you're pulling it, and you might be getting small payouts, and you know, not that I hang out in casinos, but you see it all, you know, when I'm walking through or whatever, and you see people that have claimed like 2 and 3 of the slot machines, and they're playing all of them. Well, let's say the one to their right or to their left hits it big. The gambler's fallacy then would be to think, I can't use that one because it just won. It just hit big. So it's not going to happen. Now, that's kind of a reverse of it. But that would be the gambler's fallacy, because they're basing their judgment on the likelihood of it hitting big based on what just occurred. Does that make sense?
Yeah.
Yeah.
Okay. Okay. So some examples. If you look down here, so a woman is pregnant with her 5th child. She's already had 4 boys. So she is certain that the next one's going to be a girl. Because the first 4 have been boys. So because it's not been a girl, therefore she's convinced that it's going to be a girl. Okay?
I have a question about that.
I'm sorry?
I have a question. Would it also be a fallacy to assume that it was going to be a boy since she already had 4?
That what? I'm sorry?
Would it be a fallacy to assume that she was going to have a 5th boy?
It could be, yes.
An assumption.
An assumption. Yep. Yep. But it's stronger because you're thinking, oh, when the next time it's going to happen.
Yeah.
You know, but it is that same line of reasoning. Yes, of basing the likelihood of something happening based on what really has not happened before. It's that thinking that because of X, now Y is going to happen.
Okay.
Yeah. Or Ken Jennings, if you will remember him from Jeopardy, if you even watched it. You know, he won, what, like 70-something consecutive games on Jeopardy. And, you know, he's 20 games in, so you're thinking, well, he's already won 20 times. Surely this 21st day of watching him on TV, he's going to lose. He didn't. He won another 50-some-odd games.
Wow.
So it's that thinking that because he has not lost, now we expect or think that the probability of him losing is greater. Okay? Or, yeah, you're on your way to work and, you know, we've got tons of bridge traffic going on over here. So just being confident and just sure that, you know, the roads are going to be completely backed up as they always are. So surely this morning it's not going to be that bad. Well, you know, inevitably it will be. So that's the fallacy, is basing your probability, your confidence in an event occurring based on what has happened in the short run, rather than looking at it over the long run. So there is a question about the stock market. Kind of plays into that as well. It's like, oh, what do I do? You know, this is where it is today, or this is where it's been the past 10 days. But their thinking in playing the stock markets is you gotta stick it out, because look at it in the long run. So when it tanks, you know, and you lose a lot of money, it's like, stick with it, you know, don't get out yet, because it's gonna go back up. We need to look at it over the past 10 years, rather than basing it on what just occurred. Now, if we were to compute the probability of something happening, which I'm not going to ask you all to do, what you would need to do, though, as with any other procedure or operation that we have done in here, you would create a probability distribution. And that can either be done empirically by literally sitting there and observing the relative frequency in the entire population or sample, which is not going to be very feasible. You know, that would be like sitting and watching every single car go down that stretch of market and seeing if they are going to get caught by every single red light or if they're going to make it all the way through. That's impossible to do. So generally the way it's done is theoretically, okay? And theoretically, you're going to be looking at the relative frequency based on the assumption of how it's distributed in nature. So you can see there, and we're going to do an example of it here in just a moment. The probability of an event happening is the number of ways that an event can occur divided by the total number of possible outcomes. So let me show you how that would play out.
Is that event relevant to anything?
It's probability of whatever event you're looking at. Okay, so yeah, you would actually write in there what event you would be looking at. Yeah.
Does it matter how many times there was the event?
No, it's the probability of it happening. Of it happening.
Okay.
Yep. Yep. All right, so let me show you here. Okay. So this is a probability little thing. Okay, so given that there are three colors, there's the red, the blue, and the yellow. If I were to spin it 10 times, what would you say the probability would be that we would get each one of those colors? Very good. 10 divided by 3 is what you would expect. And it's really kind of like 3.33 or whatever it is. So we would expect each one of those to occur about 3 times. If I were to spin it 10 times. Okay? So what we're going to do, I'm going to set it for 10 spins and see what it comes up with.
Does it go any faster?
Is that the first one?
No, that's the 10. It's calculated it for 10 times.
Okay.
Yeah, we're not going to do that 10 times. Don't worry about that. Okay. So what do you think about that? We would have expected maybe 3, 3, 4, right? It's not going to be exact. We would have expected about 3, 3, 4. But that's not what we got this time. So let's see if we do 10 more. We would still expect it to be a third, a third, and a third because there's 3 colors.
Depends on when it started on the color. What color did it start on before you spent it?
Maybe gravity has an effect on there, so it's yellow on the bottom.
Okay? Is that getting any closer?
A little bit.
Little bit. We would kind of expect 7, 7, 6. But that yellow one is still taking over. Now we've got more blue. We're up to 30, so we would expect 10, 10, and 10. Okay? But you can see over the long haul, it hasn't quite evened itself out yet, and I'm not going to do it up to 100. I won't put you all through that just to sit here and watch. But if we kept going with it, over time, it's going to start to even itself out just by pure chance. You know, that's what we ended up with. So what we would be doing in looking at probability of our samples would be just this. So we've already essentially done, we've got 3 samples right now. The first set of 10 spins, the second set of 10 spins, the third set, okay? And we could conceivably say, okay, we would predict, we would expect it to be 3.33. for 33 1/3% of the time, it would be each one of those colors. And what we would do would be to take our numbers and compare it to what we would expect it to be. We would expect it to be 1/3 of the time that we would get red. So in that formula then, P event, okay, on the slide, it would be P red in the parentheses equals the total number of ways an event can occur divided by the total number of possible outcomes. Well, what would be the number of ways that we can get red? How many ways can we get red in that spinner?
One.
One. We can only get red in one way, because there's only one red. Okay? What's the total number of possible outcomes in that spinner?
3.
3. So 1 divided by 3 is going to be your, whatever it is, 3.33333. Okay? Now, we could also look at this if we did like a spinner with 4. And said, you know, what would be the probability of getting a blue? So the P for a blue event is going to be 1 divided by 4.
Would that just be 1.4?
It would be, no, they would actually calculate it out. So 1 divided by 4.
It's like the calculations they use with blackjack.
We got our gambler here. That I don't know. I don't know.
I just play the same.
Yeah.
Yeah.
But then with this, you can also figure out the possibility of getting either a red or a yellow. Okay, so that would be the P, red or yellow. The number of ways that we can get that is going to be 2, red or yellow, divided by 3, because that's the total number of possible outcomes. And that's all it is for figuring out the probability. And then obviously when you calculate that out, it's going to be a percentage, or it's going to be a proportion with the decimal. So that is all that it does.
What about that, that little tinier wheel with the bigger green area?
Okay.
Because it's not divided equally.
Yeah.
So there's more chance that you can hit on the green.
So how would we figure out that percentage?
What is that? Okay, it's not giving it to me.
Oh,
Oh, I've never used that one before.
Higher probability.
But it is. It's going to be a higher probability of green because it is taking up a larger proportion of the wheel.
so we just figure out what percent of the wheel that's taking up, and then that's divide that by the color?
Absolutely. Yep. Absolutely. Yeah, the others have all been equal.
Yeah.
In
Well, that one, so if that one, instead of saying 1 out of 3, if you were talking about the green, it would be more like 2 out of 5? Or how would that, 2 divided by 5, or how would you?
Yeah. Yep. Because you would, yeah, it would be a more complex one to figure out. But absolutely, because you would have to somehow be able to figure out what proportion of the total that green is. Yeah. And because the red and the blue likewise are not equal. Yeah, it appears that the red is still 1/4. I would guess that it's probably 3/8. Yeah, I would guess that the red is probably 2/8, the blue 1/8, and the green 5/8.
Okay.
If I had to ballpark it. Yeah. Yeah, but you get the concept of what that probability piece is like. Absolutely. Okay. Now, as you all have already started talking, there are going to be different factors that are going to influence your probability. Okay? one of those is going to be the relationship between the events. So what does that mean? Well, two events can either be independent of each other or they can be dependent on each other. If the events are independent, what that means is the probability of one event occurring is not influenced by the probability of another occurring. The probability of one event occurring is not influenced by that of any other event. So let me give you an example. When my cousin, how old were we? We were probably 10 at the time. We've been going to Myrtle Beach forever with them on family vacations, and as was the norm, our parents were out golfing, and as was the norm, we would end up going down to the pool. And we had older cousins there that were watching us, so it wasn't just, those of us between about the ages of 5 and 10 running wild. Anyway, that morning, my cousin ate Apple Jacks for breakfast. Loved Apple Jacks, had them every morning. That day, when we got down to the pool, we'd been down there maybe 30, 45 minutes, and he had his first seizure. Okay? At the pool, we're freaking out. My older cousins are freaking out because the parents aren't there. Fortunately, because we were around the pool, he wasn't in the pool. He was just on the side of it, and there happened to be a doctor there on vacation as well. And so he kind of helped, and of course, then we're calling the parents, trying to get them on the golf course, to get them to come back because this had happened. Now, there's an element of conditioning to this, absolutely. But he began to associate the Apple Jacks with having a seizure. In his mind, those two things got linked. So in his mind, the probability of having a seizure was linked to eating Apple Jacks. So when you're thinking you're going to have a seizure if you eat Apple Jacks, he doesn't eat Apple Jacks and still does it to this day. And that's 30 some odd years later. He still does not eat Apple Jacks. So those are two events that were completely independent of each other. It was going to happen no matter what he had for breakfast. So that's an example of independent relationship between the variables. Okay? When it comes down to horse racing, you look at track conditions. Are they a horse that runs better in, rain and wet and muddier conditions, or do they do better in other conditions? Now, those two things may be related, but they may not. Okay? For me, there is no relationship at all, but I always bet. I don't look at the odds. I don't look at any of that. I base it on the color of the horse and the color of the silks. Those two things have nothing to do with one another, whether the horse is going to win based on its color or based on the jockey silks. But that's the way I bet. I'm not successful at it either. So I do on occasion, not often though. So those are two events that are independent of each other. Now, there are going to be other times though where the events are going to be related. And they're going to be dependent on one another, okay? So that the probability of one event occurring is going to, in fact, be influenced by the other, okay? An example of that would be if you water a plant, it is more likely to grow, okay, than if you don't water the plant. But that's also a relationship, too. If you don't water the plant, the likelihood or the probability of it growing is much less. So again, those two things are going to be related, okay? The likelihood of drinking alcohol and then driving, those two things are going to be related. The probability of having an accident increases if you've been drinking. The probability of having an accident increases if you're texting, if you're a distracted driver. There is a relationship between those. Those two things are dependent on each other. Now, another factor that's going to influence the probability is going to be the manner in which you get your sample. So the sampling method that you use. And this I described a little bit earlier when I was talking about pulling the charts from the prison. If we replace, well, with replacement, let's say there. So what that means, that once an event is selected, so we selected red out of that spinner. That was 1 in 3, okay, 1/3, 33% chance that it was gonna fall in there, 0.333 probability that we were gonna get a red, okay? If we replace that the next time and say, okay, now what are the chances that, or what is the probability of getting a blue? Still gonna be 1 in 3, 1 to 3, okay? If we put the blue back and now say the yellow, 1 in 3, because again, every possible outcome, every possible event has the same probability of occurring, the same chance of being selected, the same chance of occurring. So an example of that would be if you got a fun-sized bag of M&M with 3 red, 4 green, and 5 blue ones, okay? If you take one out, that's going to be 1 in 12 of whatever it is, okay? Just taking one. We've not specified a color, okay? If we put it back and then select another one, what are the chances of that next one being selected? 1 in 12, because you put it back. So there's still 12 possible outcomes there, okay? So as you can see then, down here, if we wanted to know, though, what is the probability of choosing a red and then a blue M&M? Because we keep putting the M&Ms back, the total number of 12 remains the same. So here is the equation then and how we would figure that out. The probability of red and then blue equals the probability of getting a red multiplied by the probability of getting a blue one, which equals 5/48. Does that concept make sense?
Can you say that again?
I got the red times the blue.
Okay, so if you're wanting to figure out the probability of choosing a red first and then a blue M&M, we've got 12 M&Ms total. We have 3 reds and 5 blue. Okay. So the probability of getting one of those 3 red ones out of all 12 is going to be 1 over 12, or 3 over 12. Because we have 3 possible red M&Ms to get. Does that make sense? Okay. But then we're going to put them all back. So now we still have 12 chances, 5 of which might be blue, because we had 5 blue M&Ms. So 3 out of 12 to get a red, 5 out of 12 to get a blue, divided by 12. You're on the wrong one. Up here. Yep, you're on the wrong one. We're not there yet. We're getting to that one. Okay? So you multiply the probability of getting a red one by the probability of getting a blue one, which comes out to 5/48. Because your 3 times 5 is 15, 12 times 12 is 144. So if we did that many times, okay, that would be our probability, because we keep putting them back. So just like I said earlier, if I pulled 1 out of the 1,000 files and put it back, and then pulled another one, still going to be 1 out of 1,000. If half the inmates were in there for murder and the other half were in there for drug-related charges that did not include murder, then I would have 500 over 1,000 that I would pull a murderer, and 500 out of 1,000 that I would pull a drug-related charge. Does that make sense?
Yes.
When I put the files back, it's back to 1,000, okay? But now, what if I didn't put the files back? What if I didn't put the M&Ms back? What if this time, instead of taking an M&M out of that 12, out of the funds pack, I took one of them and I ate it? Okay, so that was 1 out of 12. What's the next one gonna be?
1 out of 11.
1 out of 11, because now there's only 11 M&Ms left, because I ate it. Okay.
You reduced your populace.
I've reduced the population of possible M&Ms. Okay, because I'm not replacing it, I'm eating them at this point. Okay, so now the second slide then that you were looking at is talking now about the events that are related. Okay, they're dependent on the event. So when I take the one M&M out and eat it, that's now going to change the probability for the next time I go in there to get an M&M. Okay, because it's now 1 out of 11. I eat that one, now it's 1 out of 10. I eat that one, now it's 1 out of 9. Okay, but this time, because they're related, what is the probability of getting a red and then a blue? Well, it's still going to be 3 out of 12 for getting the red first, because I still have all 12 M&Ms and there's still 3 of them in there. So the probability of my choosing a red one first is 3 out of 12. Everybody gets that part. Okay, but now I've eaten that one. So now when I go in to try to get a blue M&M, how many M&Ms are left?
11.
There are 11 left. So now it's going to be 5 over 11. Does that make sense to everybody? Because now I'm not replacing it, so it's changing the probability. Okay? So then it would be 3 over 12 multiplied by 5 over 11, which is now going to be 5 and 44, as opposed to 5 and 48 that we had when they were independent of each other, when each one had an equal chance of being selected. Does that concept make sense? The probability of it all, okay? Because what that's going to do is it's going to start moving us toward seeing our sample, what we get, what's the probability of it representing the full population. Okay? All right, let's get through the rest of this chapter. There's not that much left, and then we'll take a break and we will focus on hypothesis testing, which I figure is going to take up the majority of the time anyway. Okay, now, as you can recall from last week, we talked about getting that sampling mean distribution, that distribution of all of the different sample means, okay? So that would have been like when we did the first 10 spins, okay? And I don't know what value we would have come up with. Let's focus on the reds. I don't even remember what the values were, okay? But the reds in that time were 3, maybe 2. No, it was 2 in the first sample. Then in the next sample, it increased by maybe 4. Then in the third time we did it, it wasn't that large either. Let's say it increased by 3. So now we're getting our averages or our scores for that. But those are sample means for getting the red, because we did 3 different samples, okay? So we're going to come up with this distribution, this set of scores from all of these different samples. It's the determination of the probability of getting these sample means that forms the basis of inferential statistics. So what does that mean? Well, it means that we're going to have our line and we're going to have a bunch of different distributions. okay? So each one is a different sample. So we've got this one, we've got this one, this one, this one. Let's throw another one in there right there. Okay. See, I'm switching already. Okay, so we've got this mean, this mean, this mean, this mean, and that mean, okay? So in this, if we've got 5 different samples, each one, just like all these distributions that we've been doing the descriptive statistics on, okay? We would figure out the mean for this one, for this one, for this one, this one, this one. We now have a distribution Okay, so now we have a distribution comprised of all of these sample means. So here are scores, okay? But they all happen to be the average score from each one of the samples, okay? What we're gonna do then is start looking at these sample means from our sample set and determining whether or not they represent the population mean. And as you started to see in some of the questions in chapter 6, they were giving you the means for things. And from this point forward, you'll be given that information, okay? But what we are doing ultimately in inferential statistics is we're gonna start determining whether this mean or this one, or this one, or this one, or this one is representative of the population, of the whole population, okay? So when I chose those 30 out of 1,000 inmate files, and I got my scores on the different variables, I'm gonna know that on variable 1, what the population mean is. Well, you all can't see that. Okay, on variable 2, I'm going to know what the population mean is. Variable 3, okay? Because that study had 3 or 4 different variables that we were looking at. But what I would then do is say, in my sample, on this variable number 1, this is what I got. Does this represent the whole population of inmates in medium security prisons in Kentucky? Maybe, maybe not. We don't know yet. Well, on variable 2, I got this mean, right here, let's say. Does that represent the population as a whole of inmates in medium security prisons in Kentucky? It might not. This is where we're starting to go to. What is the probability that my sample mean is representative of the population mean? Does that leap make sense to you all?
Put them together.
What do you mean, put them together?
I mean, if you're gonna try to find the average, we have to find the means for each one of those and then put them together.
We wouldn't put them together. No, they would be viewed separately. Okay, so so this is my 30 inmates. Okay. And for my 30 inmates, on variable 1, this is the mean score that I got, whatever it is, okay? But I also had a distribution like that, okay? But on variable 1, this poorly drawn is my mean, Okay, so then I'm gonna look at the mean I got for my 30 inmates that were in a medium security prison in Kentucky and find out if what I got represents what all inmates in medium security prisons in Kentucky would get on that variable. So I'm trying to figure out how well does my sample and the scores I got represent the population. Make sense? Okay, okay. So is that helping make more sense too out of the sampling mean distribution? Okay, because that's in essence what somebody would literally have to sit and do. They would have to sit to figure out this. You would have somebody visiting all of the medium security prisons in Kentucky, taking this sample of 30, getting all of the scores, getting an average, the mean. Then they would pull another 30, figure out what that would be. Pull another 30, figure that out. I mean, you can see where that would go on and on and on. The probability of getting a red then a blue, 15 out of 132 possible combinations. Okay, so that would be pretty boring. Not up my alley by any means. So generally we know this value. We know what we're going to be comparing it to. And that's where the inferential statistics is going to start coming in. The t-test, the Pearson R, the correlation coefficient. We're starting to determine whether this represents this. Okay. So in saying that then, what we are doing is we are determining the probability that the sample means then will represent the population. The sample means, as you've just kind of heard, are in fact going to be dependent on the participants in each sample, okay? And so part of that depends on how we sampled it. Did we put the files back and choose another 30, which is the ideal? Or do we keep those 30 out because we've already assessed them and go for 30 more? So on the second go round, it would be 30 out of 970. Third go round, if we did not replace them, it would be 30 out of 940. Okay? But the ideal would be to always put the 30 back, mix them all up, and pull another 30. Okay? So you can see it's an infinite number of possible samples that you could pull. So the sample means are dependent, in fact, on the participants, obviously, that are in each of the samples, as are the relative frequencies of each value occurring. So that's going to be the luck of the draw. Again, did I pull 30 murderers, or did I get 30 people that are in there for drug-related charges? Did I get 10 murderers and 20 that were in for drug-related? Did I get 15 and 15? You know, it's going to, luck of the draw. That's what it is. Now, as a result of that, you can use the sampling distribution of means to identify the probability of obtaining a particular sample mean. Okay, and there's the formula in there. It's basically the standard error of the mean is what you would be calculating. So you calculate the standard error of the mean, and then you calculate a z-score from there. Use your little chart starting on page 422 in the back of the book to figure out where in the sample it would be. But I'm not going to have you all do that. Okay, we're not doing all of that math. That is what you would do. This is kind of the underpinnings for it. Okay. So representative samples, then, as you're kind of probably getting a sense by about now, are developed using random sampling methods. The reason being the characteristics are allowed to vary. They are allowed to occur naturally. I've not manipulated anything. I've not differentiated anybody. So it's not that I know 500 on this side are going to have this particular charge and the 500 on this side are going to have this particular charge. They're all mixed up in there together. Each person has an equal chance of being selected. It's just occurring naturally. Yes, I'm picking, but it's occurring naturally. There's no manipulation. So in that case, we hope that it's at least somewhat representative of the entire population because we've allowed it to occur as it would. Now, it may or may not be. It may not be representative at all. You know, it may have been luck of the draw that on the creativity task that I did, or the problem solving rather, that was the creepier one. On the problem solving task that I managed to get the 30 inmates who were scary good at being able to figure it out, just because of the way their brain works. I did. I had 2 guys that we'd gone through all these other guys and they couldn't figure it out. I couldn't figure it out. The person I was with couldn't figure it out. We had the answer, of course, but we wanted to see if we could figure it out ourselves, and we did nothing but get frustrated with it, and we couldn't figure it out. And the other guys eventually give up till we had these 2 that, you know, of course, the guards after the fact told us why they were, and they're like, okay, you really did not need to know that. But that just made it even creepier. Literally, they were given 20 minutes to work on it, and most people gave up before that. I can't tell you how long I spent on it. It was more than 20 minutes. 2 minutes, they had it done. Yeah. Yeah.
What kind of problem was it?
I'm sorry?
What kind of problem was it?
It was one of those where you had like the rings that were all connected and you had to like manipulate them through, but it's like, okay, that won't fit through there to be able to get it undone kind of thing. Ones that drive me nuts, that I love doing, but they drive me nuts. Yeah, in like 2 minutes had it. Thank you. All right, moving on to the next one then, you know. But their brain just works so differently. So it may have been luck of the draw that all 30 inmates that had been chosen and agreed to participate and all of that, maybe they were all able to solve that, you know, in the 2 minutes or within the time frame. But, you know, that may or may not have been representative. In our sample, they were like 2 and 28, so they were not representative. But it's luck of the draw of who you get. Yeah. So, you know, we're trying to figure out how representative is our sample of the whole population. Now, as mentioned earlier, there is going to be error in that because it's not going to be a perfect representation. We'll never, and I can say that with fair, you know, with quite a bit of certainty, you will never get a sample mean that equals the population mean, okay? Because that would be a perfect representation. Just like you will really never get the perfect normal distribution, as we even saw in doing the spins, you'll get roughly normal distributions. So you'll get roughly similar, you may get roughly similar sample means to the population mean. But again, you're not going to have the perfect relationship, won't get the perfect normal distribution, won't get the perfect representation. You're just trying to get as close as possible. Okay. So because of that then, because of this sampling error that will come into play based on the sample that you have, the sample will be said to have characteristics that are either similar to the population or that are more similar to another population. Okay, so it doesn't really reflect or represent the population of inmates. It represents some other population that we don't know about, but it's not representative of the inmate. Maybe it's more representative of, you know, people in Mensa. I don't know. My brain doesn't work that way. But we know it's not the inmates in that particular case. So that's about as far as we can go then with a statement about the sample. Does that make sense? Okay, okay. All right, let's see here. We've talked about that. Okay. So because we hope that our sample is fairly similar to that of the population, we have to use certain terminology when we are interpreting our results. If our sample mean is close to that of the population, then what we can say is that we would accept or retain, and you're going to hear that word a lot in chapter 10. We either accept or retain the sample as being representative of the population. If it's not at all similar or close to that of the population mean, then we're going to reject the sample as being representative of the population. So we either accept or retain, or we reject it. And that moves us into the last slide for this particular chapter, okay? When we set up our sampling distribution of means, in theory, we can look at both the probability of getting a particular sample mean from that, and we can decide whether the sample represents the population. Going back to the standard normal curve, okay, there is going to be a value, as you kind of started to figure out from chapter 6 questions, with that z-score, it's a standard score, where does it fall on the distribution relative to the other scores? There is going to be a value on that standard curve at which the mean is either so far above or below the population mean that we do not have confidence at all that our sample represents the population. That area is going to be called the region of rejection. Okay? So we've got our standard. The glare on there is a little bit better. Okay. So we've got our standard. Can you all see that okay?
Yes.
Okay. So we've got our standard curve, right? We know our mean. We've got -1 standard deviation, +1 standard deviation. And what we're going to do is when we get it, okay, let's say that the mean for solving that problem in the general population, or in the population with our little mu sign, is 18 minutes, okay? And let's say the standard deviation is 7, okay? So with a standard deviation of 7, our range, our 1 standard deviation above is going to be 18 plus 7, right? Because we add that to our mean, which is going to be 25 minutes. And on, you know, the quickest it usually happens would be 11 minutes, because that's going to be 18 minus our standard deviation of 7. 68% of the scores falls between 11 and 25 minutes to solve that problem. Let's say though that our kind of scary group of inmates, our sample mean is going to be way down here at 5 minutes. Okay? So what we're going to be doing at this point then is figuring out how our sample mean of 5 minutes compares to this. Now we know that 68% is going to fall between 11 and 25 minutes. That's where most inmates in the population are going to be. You're going to end up figuring out the Z scores. That's going to become your what they call the critical value. So it's going to be that value at which our mean is either so far above or below the mean that we cannot say, we don't have the confidence that this 5-minute problem solving is representative of our population of inmates. Does that make sense? What we're going to be doing with all of this? Yeah? There's going to be a point that you all will be figuring out. It's probably going to be somewhere around here. So if in figuring out, let's say the Z-score for, I'm not even going to go there. So here's our little Z-score, our critical value. If this falls below the Z-score, it is in the region of rejection. Okay? This does not represent the population of inmates. We don't know what it represents, but it's not the inmates. And that can occur above or below. Okay? And in our next chapter, it's going to start talking about the prediction piece, the hypothesis, because that's what a hypothesis is. It's an educated guess based on the literature, based on the other research we've looked into. You know, they always have at the beginning of research articles, the lit review part of it. Previous experiments, previous studies have found blah, 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 blah. That's what led us to our current study, and this is what we expect to have happen. So we would expect, when we're stating our hypothesis, we would state something about what we expect to happen. And then we're going to test and see if that's what actually happened or not. It sounds complex. It kind of is, especially when we start getting into the error types and that. But this is the point we're at now, is looking at that region of rejection to say, does this represent the population? Okay. And so when I mentioned earlier the probability of 0.05, that's going to start coming into play now, actually, because the region of rejection that we choose is going to be based on the confidence that we have. Is it 0.05 or is it 0.01? There are going to be times that we want to be so certain that it represents it that we need to be even more strict with it, and we would up it to a 0.01. Most of the time, people are willing to accept 0.05 of making an error. So we want to say with 95% confidence that this is representative. But there will be times when we need to be 99% sure that what we found is representative. And again, that will make more sense when we start talking more about chapter 10. But that, in part, that value determines where we put, and the value where we start the region of rejection. Any questions about that piece of it that you can think of right now? Not yet. Okay. All right. Well, let's go ahead and take a 15-minute break then, and we'll come back and talk hypothesis testing.
I can't even get to the door.
Well, everybody's back, so let's go ahead and jump in to talk about hypothesis testing. One thing that you all will notice is that there are some calculations that have to be computed in this part. I probably will not spend a lot of time on them, only because it pulls information from previous chapters. So I think maybe at this point it'll be easier for us just to kind of run through the equation part and to focus more on the conceptual and the content aspect of it. But if we need to go through it, we certainly will. But I'm just thinking you all are probably getting really tired of hearing the sample mean, the population mean, the standard deviation, and all of that. So please let me know, though, if I need to go over them. And it looks like you all may still be muted out there.
So would it be too late to change ours? Comes back and.
No. Okay. So as you all know, as we just talked, you will pretty much never get a sample mean that equals the population mean, and the reason for that is due to sampling error. There's always going to be uncertainty in the information. So we use specific procedures in inferential statistics that is based on, as you might guess, the research design, whether it's correlational or experimental, that's going to dictate which set of inferential statistics we use, as well as the scale of measurement of our dependent variable. And the dependent variable, as you all know, is the I wonder variable. Okay? So the two categories of inferential statistics are the parametric and the non-parametric. The parametric statistics are the ones that are most often used. Reason being that it's used for a normal distribution of interval or ratio data, which is the majority of the research, especially if it's experimental, because you've kind of already made it through the correlational stages. But the parametric statistics require that those assumptions be met before they are used. Again, it's going to be preferable, just as interval and ratio data are preferable. But now there is a whole subset of statistics that are used, which are called the non-parametric. As you might guess then, the non-parametric statistics aren't as strong, but they are used for the nominal and ordinal data, or they are used for distributions that are skewed, even if they include interval or ratio data. So those aren't as strong as the parametric. The majority of what we are going to be focusing on is going to be the parametric statistics. Chances are I will probably, the very last class, run through just some examples of what the non-parametric are, so that at least you've heard the words and you've heard of them, but we're not going to spend a lot of time on the non-parametric. Okay, so how do we go about setting up an inferential procedure? Well, there are going to be several steps that we have to follow. The first thing that we have to do is create our hypothesis. And as everyone knows, a hypothesis is an educated guess. We then have to design our research study to be able to test the hypothesis. So however you would go about that is what you would need to do to test it. We then translate the narrative hypothesis into experimental notation and statistical notation. So we may have this idea in our head of what we want to test and what we hypothesize, but then we got to put it in a specific format. Okay? The last thing that we do then is we choose and set up the appropriate procedures in order to test the hypothesis. And in testing the hypothesis, we're making a determination about how representative our sample is of the population. Okay. If we have a one sample experiment, it requires that we already know the population mean. Okay. So that doesn't often occur because there's really nobody that we can call up and say, what's the population mean for inmates on this? So more often than not, it's going to be two different samples. So that's why you would come into studies such as those that we talked about early on. You know, who experiences less depression over the course of, 6 months of treatment? The ones that get medication, the ones that don't get anything, the ones that get medication and counseling. So those are who you're going to start comparing to. You're not going to compare necessarily to the population mean. Okay, so how do we create a hypothesis? Well, the experimental hypothesis describes the relationship that we may or may not find. Okay, so what's the relationship going to be between our sample and the population? One of these hypotheses is going to say that we will in fact display or find the predicted relationship. That when we manipulate our independent variable, we are going to find the expected results. Who can think of an example of that?
Medication,
Okay, what would you say about that?
that someone on medication, like on the code, is more likely to get better than someone that's not.
Okay, yeah. It's something as straightforward as that. That taking medication, when you have a cold, you would expect the person to get better, right? You'd expect them to feel better. So that is a statement of what we would expect to find. Or we would expect that the sample taking medication is going to report fewer cold symptoms than the sample over here who's not taking medication. Yeah, yeah. And as I just went into, the other experimental hypothesis is going to say that we're not going to demonstrate a relationship. So what that would look like then is that we would not find a significant difference between the people taking medication and the people not taking medication in terms of how much better they feel. So the people on medication didn't perform any better or feel any better than the people that didn't take medication. So we did not find what we expected. Do those distinctions make sense to you all? Okay. Okay. So that's our prediction then. The people take cold medicine are going to feel better than the people that don't take cold medicine. Okay. Now, when we make these predictions, because that's what that is, it's going to be in one of two ways. The first of those is that we expect a relationship but aren't really sure in what direction it's going to be. So we expect what that would say then is that we expect there to be a difference in feeling better between the people taking medication and the people not taking medication. In that statement, we've not said who we expect to feel better. Okay? So we are not making a statement of what we think. Now, we can also make the prediction and say very explicitly, we expect the people taking medication to feel better than the people not taking medication. So that's two different predictions. One, just that there will be a difference. The other one says, I expect something specific. Okay? If we're not sure if there's going to be a difference, we are now using a two-tailed test. What that's saying is we expect it to either be one end or the other. We're not going to say what we expect to have happen. If we state a direction, whether it's they're going to feel better or they're going to feel worse, we've now stated a direction, and it's a one-tailed test. Because we're saying we expect it to be only in one direction. Okay, so once we have stated our hypothesis of what it is we're looking at, what we expect to happen, the next thing we need to do is we need to take that narrative experimental hypothesis and we have to translate it into statistical terminology and statistical formulas. Okay? These statistical formulas or statements are going to describe the predicted relationships and whether the predicted relationship exists or not. So the first hypothesis, the first statistical hypothesis that we have is called the alternative hypothesis. And the alternative hypothesis is going to have this, H for hypothesis and a little A for alternative. Okay? This one is always going to be a little bit easier to state because basically what it's saying is that the relationship works as we expect. So if we expect people taking cold medicine to feel better, that's what this particular hypothesis is going to tell us. Okay? It's always going to say that a difference is going to exist. Okay? We expect medication people to feel better and be different than the people who are not taking medication. So it's saying that our independent variable, the manipulation of our independent variable made a difference. Okay? And so what we're going to do is we're going to write it just like this and say our population mean does not equal basically our sample mean. Okay? Whatever that mean would be. Okay? So there is going to be a difference between them. The null hypothesis is going to be the H with a little O for null. And it is the statement that there is not going to be a difference. So this is the hypothesis that's going to say no difference in the groups. No difference between the people taking medication and the people not taking medication. So in this case, it's going to equal whatever the means are. They're going to be the same or similar enough. Okay? But now, we can make these statements, but we got to keep in mind there's sampling error. So there's a possibility that even if we find a relationship, and even if we find a difference, it may just be because of the sample that we had. Okay, maybe we had all 30 inmates that could solve the problem in 5 minutes instead of what we would expect, which is the 18 minutes or the 11 to 25 minutes. Okay? So because there's going to be sampling error, we, again, can't prove anything. We can't state with 100% certainty that this is a true difference in the samples. So one of the easiest ways to do this is by using the z-test. That's certainly a letter that you all have heard before. So the z-test is the easiest inferential statistic to use. Okay? Basically what it does is it computes a z-score, which you all have been doing. It computes the z-score for a sample mean. and it's used in one sample experiments. So if you only have one sample, kind of like the 30 inmates, and we're comparing it to the population of inmates. The Z-test is used in one sample experiment, provided it meets 4 basic assumptions. The sample has to be randomly selected. We've talked about that and the importance of that. The dependent variable is at least approximately normally distributed, and it's interval and ratio data. All that's the preferred, okay? We know the population mean, that's a biggie. If we don't know that, then we can't do a one sample test. And we have to know the true standard deviation that occurs in the population. If we know, if we've got those 4 assumptions met, then we can perform the Z-test. So what you would do is the sampling distribution gets set up, and we determine the size and location of that region of rejection. So we figure out that Z-score that creates the region of rejection and those critical values. The first thing that we need to decide is the alpha. That is the criterion probability, the likelihood that a sample represents a population. So the alpha that we set, which is generally 0.05, I'll tell you that now. The alpha is generally going to be 0.05, and that says, you know what, this sample mean is too unlikely to represent the population. So my inmates that, you know, in our sample that were solving it in 5 minutes, that's too unlikely to have come from the population of inmates where the average is 18 minutes. That's probably going to be a different population. So then you're going to locate the region of rejection, determine the critical value, which is a Z-score. We then test the hypothesis by comparing the Z-score for the sample mean to this critical value Z-score. So you're thinking, okay, what on earth does all of that mean? Well, looking at the next slide, you can see where you start to create the Z-score. Okay, so here's our sample set of raw scores of students that are not in a study group, okay? Maybe those are scores on a test, scores on an assignment, whatever they are. But they are the raw scores of students that were attained by students not in a study group. The mean is 3.6. We're going to say the population mean is 5. And so that would be of the students who are in a study group. And our true standard deviation is 2. Our alpha is 0.05. Okay, so that right there gives us a lot of the information that we need. The total region of rejection then is 0.05 of our normal curve. Okay? Because we've not stated any prediction on them doing better or doing worse, half of that value goes into each of the tails. It's a 2-tailed test. So we've got 0.025 in the upper tail, we've got 0.025 in the lower tail. So we split it. Again, our good friend the Z table in the back of the book. We're going to look up, we're going to look for the area beyond the Z that is in the tail. It corresponds to 0.025. Right? Because that's that little part that's our region projection.
So where do we look? I'm still kind of confused on how to use this table.
Okay, okay. So the Z table, what it gives you is either you've computed or you're trying to figure out what the Z scores are. So you've got that standard score in the first column under Z. Okay. It's then in column B going to tell us the area between the mean and our Z score. What percentage of scores fall between the mean and the Z score? But you'll notice it's not indicated as being positive or negative. It's just the Z, because then it's up to us to add it or subtract it from the mean.
I still don't understand. So what's, oh, I can't see what you're writing on the board. You've got that slide up there.
Okay. Shoot. Okay.
So score is 1.96.
Okay.
The slide's still up there.
Oh, I thought you were referencing something to it.
No, I was saying I couldn't see what you were writing on the board. There you go.
Okay.
So the Z score is 1.96.
Yes.
And then it says 0.4750 to 0.0250. But what does that mean?
Okay.
And what are we supposed to be doing with that?
Right. Okay. So what you're doing is you're computing the Z test. So let's say our mean, which is 3.6. Okay, that was the mean for our sample. Okay. This is our sample mean, okay, of 3.6. This is the population. The population mean is 5, okay? So it's up here at 5. Okay, we know that because somebody told us that, okay? Standard deviation is 2. Okay, so standard deviation is going to be down to 3. Okay, from
right.
Does that make sense?
Yeah, that makes sense.
Okay, so that makes sense. Okay, now we want to be. We're only willing to accept a 5% chance of being wrong about our conclusion. Okay, we know that because we've selected our alpha. Okay, our alpha is 0.05, so that's telling us about the confidence that we want to have in our results. Okay,
okay,
and 0.05 is what's generally used. That's kind of the standard one that's used. So with 0.05 then, because we've not stated a direction in our hypothesis, we've not said that being in a study group, you're going to perform better. We've not said that you're not going to perform better. We're just saying, let's see if there's a difference in the scores attained by students in a study group and not in a study group. That's what our hypothesis is. So because we've not stated whether they're going to do better or worse, it makes it a two-tailed test.
okay,
Because we don't know if it's going to be better or worse, right? So having 0.05 then as our confidence level, 2 tails, right? That's going to put 0.025 in each of the tails because we got to split it between the 2. And that's kind of a conceptual thing.
each tail.
Mm-hmm. If it's 2-tailed, we take whatever our alpha is and we split it into 2.
Okay,
Okay? So, using then the Z table, okay? we want to look for that area beyond Z, because Z is going to become our critical value. That's going to set the region of rejection. So that's why we're looking at the Z table. It's a Z test.
I have a question.
Yes.
Okay. Okay, I don't actually see a score that corresponds with .025.
Would it be
Because it split the alpha, the 0.5, and so you put half on one end and half on the other end,
Correct.
where you get the 0.025.
Correct.
But if you're looking for a mean, like I'm looking at the A, B, and C columns, it goes 0.03.
I see a .0250.
Uh-huh. Where do you see that?
1.96.
424, the second one down. 1.96.
Where we're going with this, though.
0250, and the area between mean and Z is .750. Unless mine's different than yours, because mine's an
So you're looking at the area beyond Z in the tail. So you're looking at under column C.
I see it now. I'm sorry. I see.
Got it? Okay. Because that's the region of rejection. So it's the area from Z into the tail. Because that, again, remember our tails are the extreme scores. So is this value that we got from our sample so extreme that it can't represent the population? Okay? So you're looking under column C for .025, which is .0250 on page 424, second one down. And that equates to a Z-score of 1.96. Does everybody see that?
So we didn't look that up in the back of the book knowing what the Z-score was. We looked it up in the back of the book. We looked for the .025. Is that what you're saying?
Correct. Yeah, because that's going to be that portion in the tail that if our score falls into that, we're rejecting it. It's too different. It's too extreme from the other scores.
And we knew that we wanted to look at the .025 because it was half of that. Okay.
Correct. Correct.
So
we've not stated a predicted direction for the scores to go. So we have to take into account whether it's higher or lower, which puts it into either one of the tails.
So now what do we do with that?
Good. So the 1.96 becomes our critical value. Okay? So our critical value then is 1.96. Which is the Z crit equals 1.96. Okay? Does that make sense? That's what they call it, the Z critical value. That is just a Z score, but it represents the critical value. The critical value sets the point at which anything higher or lower than that, we're going to reject. It's too extreme, it's too different.
Will it always be the Z score?
It will always be a Z score. Yes, it will always be a Z score.
So this is what I'm getting. To get a Z test, correct? That's what we're working on. You have to find the Z score, and turn to your little temperature, find it on this column C, your Z script, and then you start rejecting.
Well, then we know what that value is.
Right.
That just tells us our value against which we're going to compare what we actually got. Our Z score of what we actually get. Okay, so let me kind of keep going through that. Okay, so then kind of taking a step back from it now, we've got our independent variable, which was study group participation. Either you were in a study group or you weren't. The dependent variable being the change in the scores, okay? So our experimental hypothesis then is going to be that group participation study group participation is not going to affect the scores. Okay? But then our second hypothesis, our alternative hypothesis, is going to be that the study group participation, in fact, will affect the scores. That's all we're saying, is that there will be a difference. Okay? So when we write that statistically, because our population mean was 5, we will say that the null hypothesis is that the population, the mean will equal 5. The alternative hypothesis is that the mean will not equal 5.
So it'll always have both of those?
It will always have both of those. Yep. You always state both hypotheses. Okay? So now, we've got to figure out what our z-score is that we obtained from our sample. We already know the critical value. So we take our sample mean, subtract from it the population mean because we know it, and we're going to divide it by the standard error of the mean.
That's 0.5.
The standard error of the mean is right down here. Okay. The formula that you all have seen before, we talked about it last week, I believe it was. Okay. So we know the sample mean, which is 3.6. We know the population mean, which is 5. And so then what we would have to do is calculate the standard error of the mean. And that's going to be the standard deviation, which I conveyed to you all. What it would be, it was 2. And we divide it by the square root of our n, which is 10.
Can we have this on the board?
Yes.
I thought the standard. Where did you
Because it was given to us over here, standard deviation.
Where?
Oh,
No, I have down 3. Oh, I see it up there now. Okay.
The z-score is what?
The decrease.
It's a secret, that's what it's a secret. It's a secret. Oh my God.
Negative 0.7, right?
Okay, so we know that our mean equals 3.6. Our population mean equals 5. Oh, that's getting close, isn't it? Our standard deviation is 2. Our alpha is 0.05, which puts 0.025 in each tail. The z-score corresponding to that is 1.96. Okay. So now we have to figure out what the z-score, our z-score would be from our sample. Okay? Because we know the critical value is this. Is this on there? Okay. So our z-score, the critical value is 1.96. So to get our obtained z-score, is going to be the sample mean minus the population mean divided by the standard error of the mean. Okay? The standard error of the mean, this bottom part, is going to be the standard deviation divided by the square root of our n, which is 10. In there. So it's going to be 2 divided by the square root of 10. And then it's worked out there, but it's going to be 0.63. Okay?
So, okay. So it's going to be 3.6 minus 5 divided by 0.63.
Yes. And so 3.6 minus 5, let me get it here.
Is
going to, so then our z obtained will be 3.6 minus 5 divided by 0.63, which equals a negative 1.4 divided by 0.63, which equals a negative, I'm going to be able to get all this in here, 2.222, two's forever. Okay. So this is the score we got from our sample. This is where our mean falls in terms of a z-score. So now what we're going to do is we're going to compare this value to 1.96.
So it's rejected?
Where does this fall compared to this?
Outside.
It's outside of it. We reject it. Okay? This score is too extreme. It's too far into the tail to be accepted. So what that means then is that we're going to reject it.
The whole thing, or?
Well, what we do is we reject it as being, yeah. It's in the region of rejection because it's beyond that critical value of 1.96.
Whatever hypothesis we would have had for that is
that 1.96 really on there?
No, it's a rejection about the differences between it, okay?
On this line?
So what it means is that our sample is unlikely to represent that of
Come over here, you're not.
the population, okay? So we say that we reject, and this is where it does get confusing because the way they write them is a lot of double negatives,
The standard.
okay?
Now ours.
And so likewise, I always have to double check myself in what I'm saying and how I'm conveying it because it's a lot of double negatives. So when we interpret this score then, what we would say, as is on the next slide, and I'm going to be very particular and I'm just going to read it straight from there to make sure that I'm saying it correctly as well. The score falls within the region of rejection because it's further into the tail. Okay, so it's a more extreme score that occurs less frequently, right? So we have to conclude that the sample, our sample, is unlikely to have come from and represent the population where there is a mean of 5. Okay? So what we're doing is we are rejecting the null hypothesis. So when we reject it, that there is no relationship between our independent variable and the dependent variable. So we reject Okay. So our hypotheses, the null says that it will equal 5. The alternative says that it will not equal 5, that there will be a difference. No difference, difference. When we now put it into a narrative format, our null hypothesis says that the study group participation will not make a difference. Okay? The alternative hypothesis is that it will make a difference. So, because we are always testing this one, even though that seems kind of silly because this is really what we're wanting to find,
Yeah.
but we're always testing the null hypothesis. We've just rejected the null hypothesis. Okay, because okay, this was further into the tail than this. Okay, so we are rejecting this. We are rejecting the idea that there is no difference. So if we're rejecting the idea that there's no difference, we are accepting this one, that there actually is a difference. So the way we interpret that then is that study group participation makes a difference in the scores.
But it doesn't say whether they make a positive or negative.
Correct, correct. Because we didn't specify that.
Right.
We just said it would be a difference, so we had to split it into the two tails. Okay, we didn't state that it was going to make, you know, that the scores would be higher, that the scores would be lower. We just said there's going to be a difference. Exactly. Questions about that?
Which the fact that it's better doesn't make it a positive difference.
Right, we can't say that. We have to be very cautious in what we do say in making our interpretations. Yeah, yeah. We can only go so far in the statements. Yep. So by accepting this, it says that there is a relationship between study group participation and scores. Questions on that? around in your brain. Okay, okay. Let's get through, let's at least try to get through the, well, let's see how far we get tonight. Okay. Now, have you all heard this concept about research findings being significant or not? Do you all see that in like the articles that you read, or have you heard people talk about the results are significant?
Right,
Okay, what does that mean to you all?
that they're important.
That's what a lot of people think, is that it's important, but that's not what it means. Not in,
Actually, that
Yeah, either.
we have to.
yes.
Or investigate.
Did you all hear what Julia was saying?
No.
No,
Repeat that, Julia.
That it makes enough difference that we have to investigate.
Yeah. That the
You know,
dip,
look a little deeper.
yeah, the difference was big enough between the study group, or, you know, their participation in a study group. That difference in means between our obtained score of 3.6 and the population mean of 5, that difference was big enough that we can say it's significant. Okay, it doesn't mean that it's important, because we can find significant results on really inane things. Doesn't mean it's important, just means it's different enough that there is a difference, okay? And that it's not solely due to chance, okay? So significance is obtaining a result that is unlikely to occur if the predicted relationship does not exist in the population. So the significance is saying that the relationship we found is believable and not just the result of sampling error. So that gives us confidence in what we're saying. We have greater confidence with this significant result to say study group participation makes a difference. There is a relationship between study group participation and assignment scores. Yeah. When we're doing the Z-tests, the decision about significance is yes or no. Either it is in the region of rejection or it is not. You know, that value could have been 1.97, and that is going to be just as significant as our 2.222. It's yes or no.
The Z score takes away any gray area.
Yeah, yep, the Z-score takes away any gray area. So our Z obtained and the Z critical value, whoops. Okay? It's yes or no, either it's in the region of rejection or it's not. Now, as we mentioned, we can only go so far, though, in our interpretation of this. When we now take the statistical and we translate it back into a narrative form. Some things to keep in mind, okay? There's no proof that our null hypothesis is false. So we can't say that that's not true. All we can say is that with our sample, this is what we found. So all that's been proven, so to speak, is that it's very unlikely that the sample mean of 3.6 came from the same population having a mean of 5. There's no proof that the independent variable caused them to change. All we know is that they're different. There could be other variables at work. So as was highlighted in here on the paper that you all turned in that I've got to get scored, everybody, I'm sure you don't know what the confounding variables are. And so if you were able to answer it, great. If not, that's okay too. Nobody's gonna have points deducted for that.
I,
But that's when it talks about the other variables that may be at work, that made me think about the confounding.
can there possibly be two meanings for that? Because when I looked that word up, like I looked it up in our book and it said one thing,
Which word?
confounded.
Confounding?
Mhm. But I looked it up on the internet,
Mhm.
and from what I read, it sounded like it was saying that confounded variables can offer something that you didn't think about.
And that's why it's a problem.
Right.
That's why it's a problem.
Yeah, because when I did my
Yep.
paper, I said the confounded variables I'm concerned about are maybe there are children eating the breakfast who are allergic to eggs and don't eat,
Mhm.
or the
Yep.
children who have just had a few bad days, not having anything to do with whether or not they had the
Correct.
balance. Right.
Right. Could be the same thing here. A confounding variable could be that it has nothing to do with the study group status or participation. Maybe it was that particular group was all up late the night before. So when they came in and tried to do the assignment, they didn't do as well because they were fatigued. Had nothing to do with whether or not they were in a study group.
In the book,
So-
the definition was just completely different.
It makes it a little bit more confusing.
Yeah.
Yeah.
Because here it says that it's a confounded comparison, and the word comparison
Yeah.
made it different for me.
Yeah.
And in a two-way ANOVA.
Yep, but we're not doing the ANOVA.
Right, so it means the same thing even if you're not.
Yes, a confounding variable is a confounding variable.
Okay.
Yep.
Okay.
Okay, we've talked about the sampling error that may be contributing to the difference. And that's about it. That's about as far as you can take it, because you can't prove anything or make any other real definitive statements about it. So, what if a result is not significant? Sometimes we've got some very important things that we're studying that yield non-significant results. And it's important here, the terminology, to say either not significant or non-significant, because it's not insignificant, okay? So those are very different terms when it comes to statistics. So if it's not significant, that says that it is more likely that the result we got was due to chance or error than representing a true difference. Yeah. So when our score does not fall in the region of rejection, it's likely to be obtained frequently enough that it can probably represent the population mean, or this, that population. Even if it's a result of sampling error, it happens often enough that we can say it's part of the population and it represents the population. And so if that happens, we accept or retain the null hypothesis, that in fact there is no difference. So even if we get a non-significant result, we can still only go so far in what we say about it. We cannot say that the null hypothesis is true. It's kind of the flip side of that. We can't say that. We can't say that our independent variable of study group participation didn't have an effect. It still may have had an effect. We just don't know that. There's all we can say is that there's not enough evidence from our sample to suggest that relationship. Again, we know that sampling error probably did result or contribute to the results. and we don't really see the relationship being there. Now, real quick, I know you all are probably getting tired with this tonight, and trying to figure out the errors in statistical decision making. I'm going to put that off until next week. But I do want to quickly cover the one-tailed test, because it's very similar to what we did with the two-tailed test. The only difference, if you'll see in the handout, is that now we're going to predict a direction. We're going to predict what we think is going to happen. And in predicting the direction, so if we predicted that, in fact, study group, or that the people not in a study group would do worse, or that the people in the study group would, in fact, do better, we're now giving it a direction, okay? So what our experimental hypotheses are going to be at that point, if we state a direction, is that not participating in a study will decrease the scores. That's our alternate. And our null hypothesis then is going to be that not participating in a study group will not affect the scores. Because that's what we're measuring. We got this sample that was not in a study group. So then we also change our statistical hypotheses. Now, instead of saying that it equals or it doesn't equal, we are going to say that it is less than or greater than our sample mean, or our population mean. Okay? So our alternative hypothesis is that our mean will be less than 5, because the alternate hypothesis is that, in fact, not participating in a study group will decrease it. So we're expecting our values to be less than 5. And the null hypothesis would be that there is no difference. And so if there's no difference, our score then would be equal to or greater than that mean of 5. Does that make sense? When you state a direction, you're now going to use the greater than or less than, because you're saying what you expect it to be. Not just that it's not the same, but you're now stating whether it's going to be greater or less than that mean.
Couldn't you have said that that those participating in the study group would have a greater score?
Yes. Yes. You absolutely could.
This
Yeah.
language seems like it's developed to keep you confused.
Well, and that's where it kind of gets in a little bit into really being specific at defining what it is that you're saying. Because you absolutely could. You could have phrased it that, in fact, that you expect the study group participation to have higher scores. Yeah. So it depends in that case on who was in your sample. You know, if you had people that were in the study group in your sample, you would expect them to do better. But in ours, we had people not in the study group, so we're going to say the people not in the study group are going to do worse, or their scores will decrease. But yes, you could absolutely say that. And then, because we've stated a direction, in this case, we're stating that it will decrease. Our alpha is going to be the same at 0.05, because that's the standard alpha that's used. But what's going to be different this time when we figure out our z-score?
So I have to put it on one side.
We're only putting it on one side because we've now stated a direction. Very good. So it's now a one-tailed test. So here's our computations again. Our alpha being 0.05, so now the total region of rejection is 0.05. All of it is going to go into one tail. So now when we go back to use our z-table, the area beyond the z in the tail, which is that column C, because we're looking for that portion of it, What corresponds to 0.05 is a z-score of 1.64. So that is now our critical value.
.0505.
In column C.
Okay.
Okay, we're looking for that part in the tail. Because that says it's so extreme. Is everybody good with finding that value and how we got that?
Yes.
Okay. Whoops. And so then what we would do is we would calculate again our obtained z-score, which is going to be exactly the same, but just now we're going to compare it not to 1.96, but to 1.64. And so the other thing that you'll notice is that when we do a one-tailed test, our critical value is lower than our two-tailed test. And really, the one-tailed test is preferred than the two-tailed test because it's kind of saying we're far enough in this area to be able to state a more specific prediction. So doing the one-tailed test tends to be preferable. You all feel like getting through the last little bit? Are you still trying to absorb the whole critical value, region of rejection? What does that mean? How do I interpret the hypotheses? How do I state them? Not only narratively in the experimental form, but also the statistical form.
Yeah. My brain's gone.
Brains are gone? Okay, well, let me look. For next week then, the questions. Oh, that's what I meant to print out. Was my revision.
I don't have it.
Here it is.
Awesome.
The 928 is still chapter 10.
Okay.
Read chapter 7.
Yeah, so for next week then, chapter 9 and 10 questions are due. Let me double check that on here. There we go. Okay, so on chapter 10, it's questions 12, 14, 16, 22, and 24. Let me see if any of those deal with the hypothesis testing. So the questions for chapter 10 are going to be 12. Okay, that one's all right. 14. Okay. 16. Okay, you all can do 16, 22. And 24. Okay, I think all of those are good. None of them specifically go after the, so none of those deal specifically with, well, actually one of them does. So if you all find, if you want to take a stab at doing the errors in statistical decision-making, feel free, but don't feel like you have to do that particular part because we've not gone over it.
What part is that?
About the statistical decision-making, there is going to be, where was it? Identify the statistical error that each researcher may have made in number 22. If you want to take a stab at it, that would be great. But if you don't, because we've not gone over it, don't feel like you have to do that part.
So we don't do chapter 7?
No, we're going to get to that.
Okay, so we just do
Yeah.
chapter 9 and chapter 10.
Chapters 9 and 10. Yeah, for the questions.
If we made it with the chapter 9 question.
Yeah.
22.
Yeah, we did chapters 9 and 10 today, so chapter 9 and 10 questions are going to be due. And then I have you all reading chapters 7 and 11, I believe. Those are going to, because you've made it through this part, those will be a little bit easier to get through than for next week. So that's going to go over, I believe, the Pearson-R correlation coefficient, and then the beginning, I believe, of the t-tests. So any questions about what's due next week? Okay, so then we'll start next week with talking about the decisions and the errors in statistical decision making, and then we'll jump into chapters 7 and 11. Okay. All right, so let your brains rest.
I'm on my way home. You don't need any?
No, we're good.
Sure?
Not yet, anyway.
Okay.